All right. Hello. Here we are. Day one of Stat 512. Yeah, here we are, day one, and, we're reading this introductory slide, and it says chapter five, right? So we may be tempted to just be like, well, what the kata? Like day one, how are we already at chapter five? And so it's maybe worth addressing. Um, Stat 512, at least, kind of the way we're doing it now, the way it's typically done. It This class is typically taken in the second semester of your first year. Um, the typical 512 student, which may or may not be you, has usually just taken Stat 511 and also Stat 505 and maybe Stat 503. Now, those three classes that I mentioned, we do our best to kind of show how that material relates to the larger world of statistics. But that said, the exposure to what we would think of as like actual applied statistics in your first semester is relatively minimal. And so here we are, right? This is why we're taking the degree. We took the degree because we want to learn statistics and we need the tools. And the first semester helped set you up with those tools. And then now here we are, right? This 512 is kind of like the core of the program. If you look at the catalog, most of our graduate classes, like that sort of key pivotal fundamental prerequisite is 512, because 512 is where we're going to learn kind of like the basic building blocks of statistics. So, right, even these building blocks need some preparatory material. That was that first semester. That's the 511. That's the 505. Although technically 505 is not a prereq. So if you haven't taken it, don't panic. You'll be okay. If you have taken it, I think you'll get more out of this class. Certain parts of it might be a little bit more intuitive, but I will make sure that if you have not taken 505, that you could still understand the big picture ideas. What's important to be able to kind of do these types of statistics in kind of an applied work environment. Now, 512 has this sort of hidden prerequisite. You were probably made aware of it in Stat 511. I probably made you aware of it over your winter break. And that is, it's sort of assumed that you have a basic knowledge, a rudimentary grasp of kind of like very basic statistics, like what you would maybe take in like a general education, undergraduate, non-math major statistics class. Some of that stuff I'm sure all of you have had exposure to. A mean, a median, a mode, right? Um, even things like a histogram, hopefully, are all things that we're familiar with. Now, in my experience, the important topics that some of us maybe are not familiar with, or right, maybe are familiar with, but so rusty that we may as well not have had exposure to it, is the ideas of hypothesis testing and confidence intervals. And so I have posted on D2L like a whole bunch of kind of again, I guess preparatory material for you to work through. That's essentially chapters 1 through 4 in our textbook. Now, our textbook kind of covers them in a way like I do, like very kind of broad, very big picture, intended more as kind of like a reminder than an actual teaching someone from the ground up kind of approach. If you are someone who hasn't had any exposure at all and you would like, some other textbook suggestions, feel free to let me know. I can help you out with that. But it is important. The class is it's gonna start pretty simple, I hope. That's my goal. But it's gonna ramp up, it's gonna ramp up, it's gonna ramp up. And so if you have not had the exposure to that early introductory material, then you need to get on top of that. And it's not something that you should ignore. I've taught this class a lot. At the end of the class, I look at my gradebook. Some students do well, some students do less than well. What do the students who do less than well have in common almost without exception? What they have in common is that they struggle with that kind of hidden material that I'm assuming that you know. And I understand that assumption is not for everyone. And so it becomes, unfortunately, a little bit on you. I've put material on D2L to help. I put a lot of material on D2L to help. And I have office hours, and we have graduate assistants. There's a support structure in place. But you cannot ignore that material. If you do not know what a 95% confidence interval is, you're going to be in trouble. If you don't know what a hypothesis test is, you're going to be in trouble. And so it's really important that you make sure you feel comfortable with all of these ideas. And there'll be sort of comfort checks, not so much this week's lecture, but kind of second and third week lecture. I'll start talking about how some of that hypothesis testing and how some of that confidence intervals kind of fits into our 512 framework. And as I say that, you could say, okay, I get it or I don't get it. And hopefully you do, but if not, maybe you need to go back, if you haven't already, to that review material that's on D2L. All right? I can only do so much. I have the material there. I love talking statistics. I would love to hear from you. You can't just ignore it and hope it goes away, though, is what I'm saying. It's really important that you go through that review material, the stuff that I put there, and that you understand it, because we will be using it. And those kind of important ideas are going to be even more important as we kind of move through this material. So where chapters 1 through 4, chapters 1 through 4 are in the review material on D2L. And here we are, day 1, for better or for worse, fair or not fair. I think you'll still find this an extremely straightforward lecture. I think if anything, you'll be bored. But I do promise that the sophistication will ramp up fairly quickly. And I think that should be a good thing, right? I mean, we're here to learn. We're here to push ourselves. We're here to be interested. We're not here to be bored, right? But I also do want to kind of ease us into things. And so that's kind of what we're going to do with this lecture. So that's a whole lot of words for a single slide. Let's go ahead and try another one. So often statisticians, often researchers, right, are interested in testing the possible relationship between two variables. You have these two variables, and we think they might be related to one another. Often, we have something that we think of or refer to as an explanatory variable. And the other variable, we refer to it as a response variable. Some other terms that maybe you've heard is sometimes these things are referred to as a independent variable. That would be our explanatory variable, and a dependent variable. That would be our response variable, right? The idea the response variable depends, makes it a dependent variable, upon the explanatory variable, which is independent. Sometimes statisticians, mathematicians love abbreviations. So sometimes we just abbreviate these things with a single letter. So, right, if we wanted to abbreviate an explanatory variable, what would we abbreviate it with? Yeah, the letter X, of course, right? Because X is in the word explanatory. And if we wanted to abbreviate the response variable, what letter would we use? It's like a symbolic abbreviation. Of course, we'd use the letter Y, right? Because Y comes after X. So here's an example, right? We might be interested in, and you're going to see hundreds of examples before 512 is over. But here's our first of many. We might be interested, right, as researchers in exploring the potential relationship between the amount of time that someone exercises and their cholesterol. Right? Is there a relationship between it? Yes or no? And if we decide the answer is yes, how can we go about maybe quantifying or describing that relationship? Now, the world's not usually as simple as just two variables. We often have many, many other variables in play. Lots of terms for these other variables. I think our textbook, or at least the textbook I was working with at the time I made these PowerPoints, referred to these things as lurking variables. So a lurking variable is any variable other than the explanatory variable that might also explain the response variable, right? These are these variables. They're not necessarily part of what we're focused on, but nonetheless they're sort of lurking in the background. I know, very ominous, right? These kind of like shark variables. Watch out. There's other terms for them. Sometimes they're referred to as confounders. We'll talk about the idea of confounding in more depth, kind of towards the tail end of the course. So here's a second example, right? Maybe we're interested in trying to determine whether or not a vegetarian diet, right, that presence or absence of meat, helps reduce heart disease. Oh, are any of you vegetarians? Any any vegetarians in the class? Oh, very cool. So, um, what I want you to do, pause this video, right? It's the beauty of technology. Pause this video. Oh wait, I guess you can't hear me now if you just pause it. All right, hey, don't pause it just yet. I'm still getting the hang of this. So what we're gonna do, I'm gonna ask you a question, um, and then um, and then you're gonna pause it and answer that question. So in this example, think about what's the explanatory variable, what's the response variable, what are the lurking variables. Okay, I'm gonna scroll to the next slide. So pause it and write down your answers, and then here we go. Yeah, so our explanatory variable would be right, the diet. Are you a vegetarian? Yes or no. Um, right, that type of variable, one that takes only two outcomes, is sometimes referred to as a dichotomous variable. Um, oh, our response variable is heart disease. We didn't really get explicit about how we measured that. Maybe we just measure it yes or no, right? Do you have heart disease? Yes or no? Have you had a myocardial infarction? Yes or no? But I don't know. Maybe it's something a little more subtle. Maybe we're measuring blood pressure. Maybe we're measuring like some amount of like plaque buildup in the arteries, right? Those would be numerical measurements. So, for this example, we're keeping it relatively straightforward. But I mean, that's always a big part of statistics is we have this concept, heart health. How do we measure? How do we sort of best measure this concept? Now, lurking variables. What are the lurking variables? Lurking variables are variables other than the response variable, right? Lurking variables are variables other than, I'm sorry, variables other than the explanatory variable. So variables other than diet, well, other than, right, whether someone's vegetarian, because that's the aspect of diet that our explanatory variables focusing on. That might also impact our response variable. That might also impact someone's heart health, right? And certainly exercise, right? Allegedly, that's good for your heart. Smoking, right? Allegedly bad for your heart. Other aspects of diet, right? You could be a vegetarian and still, right, just go to town on a bag of Doritos. You could be a vegetarian. You could still be chugging these Monster Energy drinks, these Red Bulls, right? And that may or may not be good for your health. Probably not. And genetics, right, always kind of seem to play a pretty pivotal role in like these types of issues. So, and I'm sure you have plenty of others as well, right? So I mean, that's just sort of like the tip of the lurking iceberg that, right, if we're not cognizant of, if we're not careful of, right, might sink the might sink the Titanic of our higher learning experience. So, in the review material, right, I sort of talked about we have this sort of statistical problem, or we have some data. Maybe that's a better way to look at it. We have some data. We want to explore that data. We talked in the review material sort of two ways you could do it. You could do it sort of graphically, you could do it sort of numerically. We said often, right? It's convention to start with a graph. A picture speaks 1,000 words. The graph kind of gives us like a little bit of like a big picture insight as to what's going on. And then we can kind of drill down to get like a more detailed idea. And we often do that sort of second level of drilling down, all right, by looking at sort of numerical ways of summarizing the data. Same idea here, right? So right now, the situation that we're working in is it's referred to as bivariate data. We have two variables, right? So we have an x and a y. And so bivariate data, two variables, we might be interested in exploring a bivariate relationship, or relationship between these two variables. Probably the most common plot or the most common graphical summary when we have two quantitative variables is referred to as a scatter plot. Scatter plot, very straightforward, very simple. You just make this sort of like plot on the sort of XY axis, right? The x-axis is our x variable, that makes sense. The y-axis is our y variable, that makes sense. So every person in our study, every element of our study, right, has some x variable, some y variable, and we use that to sort of plot their location in the scatter plot. So here's a pretty straightforward example. Maybe we're interested in helping someone test their claim that a person's height could be used to predict their weight. And so to test this claim, we measure the height and weight on 10 different people with the following results, right? So the first person that we sampled, they had a height of 60 inches, a weight of 110 pounds. Next person had a height of 61 inches, weight of 105 pounds. I think these are fabricated numbers for what it's worth. I think I fabricated them long ago before I got older and chubbier. I'm not really sure how realistic these numbers actually are, but I don't know. Let's go ahead and roll with it nonetheless. So there's our data set. Right, we should be familiar with the SAS code and putting it in. Sometimes in class I get a question like whoa, what the cut though? What's going on? What's that cards statement, right? I think in 5.11 you maybe use like what, the data lines statement? Is that what maybe you put there? I don't know. You newfangled new age statisticians, right? Old fogey me, old man McClintock uses the card statement. That's what I was taught. It's what I grew up with. It works just the same as the data line statement. So it turns out there's a few different keywords you can use to kind of do the same thing. I was told, I'm not so old that I was part of the day that I've been told exists, where there were like these punch cards, whatever a punch card is. Like, we're used to punch cards, right? You get 10 punches, you get like a free sandwich at Subway. But I don't know, back in the day, punch cards were things that you used to like run computers, I guess. And you would like put the data on a punch card maybe, and maybe you would like put the instructions about how to analyze the data on like another punch card. And I don't know, you put these cards in a computer and something happened, I guess. It gave you an answer. And so someone came up with this card statement, because I guess that's like at the time it was like this kind of passing of the torch. And the people that taught me, I think, had familiarity with those computers, so they taught me this word. And I guess I'm going to use it, but probably you're going to keep using data lines like the great Professor Rieger or whoever taught 5.11 taught you. And that's probably just as good. So there's our data. Nothing new to us there except for the card statement. And we want to plot the data. We want to make a scatter plot. There's lots of procs in SAS to do that. I believe at the very last class, or close to last class of 5.11, you actually do a little bit of graph making, plot making. So you might be familiar with this proc Gplot already. There's other versions of it that are a little bit nicer. We'll talk about proc sgplot. Maybe it stands for super Gplot. I think maybe next lecture. So I'll show you other ways of doing plots. This is like maybe one of the kind of most bare bone basic ones. There's a plot statement within the proc, and you kind of specify your variables. Maybe a little unintuitively, you do the y variable first, x variable second, and connect them with an asterisk. All right, and so there's our plot. That should be straightforward. You should be able to see how that slide with the numbers, right, 2 slides back, the actual height and weights, translate to the graph that we're looking at here. All right, we had our whatever it was, 105-pound person with the height of 61 inches, right? We see them over there in the left-hand corner. So that's how we do a scattergram, or scatterplot, sometimes referred to as scatter diagrams. What do we do with these things? We make it, that's pretty cool, but once we make it, like, who cares? What's going on? What do we want from it? Allegedly there's information in here. What is that information? Well, we can use a scatterplot to describe the form, the direction, and strength of a possible bivariate relationship. So what do we mean by each of these 3 things? By form, this is almost like playing that like really fun game, like connect the dots, right? Did you ever play that as a kid? You have all these dots and you connect them and you're like, oh, look at that, cool. It's like a flaming cactus, or like a snowman with a shovel, or whatever it is that you just created with your connected dots. That's kind of what we're doing. Although, right, we don't see anything quite as cool as that. We usually say this looks like a line or doesn't look like a line. This looks like a curve. It doesn't look like a curve. Maybe it just looks like random scatter. Looks like none of the above. Those are usually the type of forms that we're looking for in a scatter plot. We can look for the direction of a relationship. Is the direction positively associated or negatively associated? We'll talk about that in just a little bit. And then sometimes we look for the strength of a relationship. That is, how closely do the points follow the form that we think we're observing. Yeah, so here we are. We talked about form, lines, curves, right? Just a bunch of just kind of randomly scattered points. So we'd call that maybe no form. Our class is going to focus for the most part on lines, what we would call linear relationships. Certainly these first few lectures are. But it is worth being aware of the fact, right? Even as we're for now focusing our attention on linear relationships, we should certainly be aware of the fact that of course there's more complicated relationships in life, what we might think of as curved relationships. Here's an example of a curved relationship right here. So I simulated this data. I think you do a little bit of simulation in Stat 511. Maybe we'll talk more about simulation down the road. But kind of just ignore the X's and Y's. It's not real data, so the numbers on the axes aren't that important. Right, for what we're talking about now, for pedagogical purposes, we're just interested in that shape and that form. That form is a curve. We call that actually a quadratic shape. I graphed a quadratic function is actually what I did there. And there are plenty of sort of real life situations, real life phenomenons that would follow a shape like that. A few years back, you may or may not be basketball fans, but I was reading an article. The article was talking about the relationship between X, the height of a basketball player, and Y, the age that basketball player retired at. And the graph actually looked a lot like this graph right here. Maybe surprising, maybe not surprising. It had that sort of quadratic curvature. So let's think about that. Like, with this example, does that make sense? Well, it makes sense that it would go up certainly for a while, right? That is, being tall is good in the game of basketball. And, right, height is something that sort of stays with us. So unlike something like quickness, like hand-eye coordination, reflexes, right? Those are things that at a competitive level, right, start to degenerate quite early. We're not quite as quick maybe at the age of 30 as we were at the age of 20, but we're the same height, right? Our height hasn't changed. So if being tall is part of what makes us good at basketball, well, that's not going away as we get older, so it lets us play the game longer, right? So it makes sense that, right, that taller basketball players can play longer. That means they have an older age of retirement. But what's kind of interesting is there was this kind of flattening out stage, and I kind of think, yeah, my memory's not what it used to be. I guess memory's one of the things that also deteriorates with age. Um, but I think it was around 7 feet. So around 7 feet, that sort of upward curve kind of started to flatten out and then go downward. And that maybe makes a little bit of sense, right? So like, if once you were like 7'1" 7'2", 7'3", it actually started to have like a little bit of a negative relationship. At that point, the taller you are, the sort of less time you would play basketball. And maybe that makes a little bit of sense, right? I mean, you think about, there are quite a few like basketball big men that were sort of like forced to retire at an early age, right? Yao Ming, Greg Odom, yeah. And plenty of others. That were, they were like star basketball players, but they didn't get to play that long because of why? Because of injuries, right? Apparently, it turns out that, I mean, at some point you get sort of so big that you become injury prone, right? And these injuries, right, force you to retire early and kind of create like an interesting shape like this. Now, of course, there's not a ton of basketball players that are 7 feet and higher. So, right, the plot of the basketball data would be much more sparse. That is, there'd be a lot fewer pluses on the right-hand side of this quadratic curve. Most of the basketball players are probably between 6 foot and 7. Probably not a lot of the 6 foot stage. So we might imagine a little sparseness at that left part, a lot of sparseness at the right part, and maybe right in our basketball data set, a concentration of points, maybe between like, I don't know, 6.5 and 7 foot. All right, so again, I just want to kind of make us aware of, that there are more complicated relationships out there than the ones that we're going to be focusing on for just the first couple weeks of the class. I promise you, we will learn how to handle situations like the one we're looking at well before 512 is at its end. So that's form. What about direction? Direction typically is focused on linear relationships. But you can have curved relationships that like don't change direction, like the one we were looking at. You can have curved relationships that, right, stay positive, at least over the kind of range of values we're looking at. You can have curved relationships that, right, are sort of decreasing, at least over the range of data we're looking at. This is pretty, I think, basic algebra. Right, a positive relationship means what? It means as x increases, y tends to increase, right? Now, that word tends is important, and I want you to use it. You'll lose points in class if you don't use it. Right? Statistics is different than math. In math, you have, right, these deterministic relationships. In statistics, we're dealing with real life data. And when we're dealing with real life data, there's almost always exceptions to whatever rule we think we're observing. We're observing tendencies, right? Not not like ironclad rules, not destiny. And we want to communicate that with, right? We don't want people to come away with a really strong, like a stronger sense of certainty than they should have. There's always uncertainty in statistics, and we want to use the appropriate language to communicate that. So we're not going to say as x increases, y increases. That's what you might say in math class. We're in stats class. In stats class, we're going to say as x increases, y tends to increase. You can also flip it the other way, right? You can say as x decreases, y tends to decrease, right? I mean, the idea of a positive relationship, right? The big picture idea of a positive relationship is what? Well, I mean, think of your relationship with like your BFF, right? Your best friend forever, your buffa. How would you describe that relationship? Well, when you're happy, right? When your fortunes increase, isn't your best friend also happy with you? Heck yeah. And when your fortunes decrease, when you're sad, when you're down, isn't your best friend right there with you, feeling down with you as well? What is it they say in statistics? There's a saying in statistics. It says a happiness shared is a happiness doubled, and a sorrow shared is a sorrow halved, right? And that's what we're seeing. That's a positive relationship. I describe that as a positive relationship. Whatever you do, your best friend does too, right? Positive relationship means what X does, Y does. They travel in tandem, or right? I don't want to lose points. They tend to travel in tandem, right? And of course, the opposite of that's a negative relationship, right? A negative relationship is what? Like you think of your relationship with like your evil twin, right? Or your worst enemy, right? Your arch enemy. When your fortune increases, when you're at the top of your game, right? Oh man, nothing makes your evil twin more miserable. They can't stand to see you happy. Sounds like a pretty toxic relationship to me. Maybe we'd describe that as a negative relationship. Right on the flip side, right? When you're having a bad day, right? When the quality of your day decreases, oh man, nothing makes your arch enemy happier, does it? Yeah. What's a negative relationship? It's like the relationship you have with your evil twin, right? With your worst enemy. Whatever you do, right? They do the exact opposite just to spite you. That's a negative relationship. It's toxic. Right? So those are the two relationships of the statistical world, right? And particularly when we're dealing with lines, right? Every line's gonna fall into like one of these two camps, unless we'll talk about the idea of like sort of perfectly flat, which would kind of indicate no relationship. And so we've done form, we've done direction. The last thing that we would need to do is the strength of a relationship. So the strength of relationship is, right, how strong is it? What do we mean by the strength of relationship? What do we mean by a relationship being strong? Basically, that's the idea of looking at the form that we think is being approximated by the scatter plot, and looking at like how tightly packed our points are about this form. So if all the points in our scatter plot are very, very tightly packed around a line, we say that's strong. If they're very spread out from a line, we'd call that diffuse or weak. Say that it's not very strong. It's a weak relationship. Now that third one feels like a little subjective, doesn't it? And we'll look at lots of scatter plots over the course of the class. And we'll actually look at one just a few slides, and we'll see that you definitely can look at a scatter plot and get a sense of like, is this strong, is this not strong? But you still might imagine like gray areas where it's kind of like not really sure. Like, is this strong? Is this not strong? And even more so, you might imagine like two scatter plots right next to each other. And if you tried to ask the question, which scatter plot maybe demonstrates a stronger relationship, it would be hard to answer that question. Right, so we will see. You can look at a scatter plot and get a sense just from that alone of kind of like this kind of subjective idea. It's sort of strong, it's not strong, and that's useful. But there are also cases where we would like to have more precision, something a little less fluffy and a little bit more concrete, more black and white, more objective. And that's where we transition from graphical summaries to numerical summaries. And probably one of the most important numerical summaries for exploring a linear relationship is referred to as the correlation coefficient, right? Correlation coefficient, often abbreviated by statisticians with the letter R. Of course it is, because the letter R, right, occurs twice in the word correlation. So of course we're going to abbreviate it with the letter R. And the correlation coefficient is a numerical measurement of the strength and direction of a linear relationship, right? That's one of the limitations of the correlation between X and Y. Some facts about R. R is unitless, right? So things like the mean, the median, and mode, those are in the original units of your variable, right? So if you're talking about salary, right, the mean salary is going to be in units of dollars. Correlation is a little bit unusual. There are other statistical measurements that don't have units, but not a lot of them. Correlation's one of the few. You can prove mathematically that correlation is always bounded between -1 and 1. You can't have a correlation of -12, can't have a correlation of 5,000. Someone tries to tell you that oh, I just did the most awesome statistical analysis. I got a correlation of 5,000. I don't know. They might be trying to scam you. Pretty intuitively, if the correlation is negative, somewhere between -1 and 0, that's going to indicate a negative linear relationship. If the correlation is positive, somewhere between 0 and 1, that's going to indicate a positive relationship, right? So that is how correlation tells us the direction of a linear relationship. Correlation can also tell us the strength of a linear relationship. How does it do that? The closer the correlation is to 1 or -1, the stronger the relationship, right? If it's close to 1, that's a strong positive relationship. If it's close to -1, that's a strong negative relationship. In fact, the correlation will only be 1 if you could draw an upward sloping line that exactly hits every point. So a correlation of 1, that's like what we see in math class. You don't observe that in real life very often, maybe never. But we do see it in math class. So a correlation that's sort of perfectly 1 means you can draw an upward sloping line, a positively sloping line that hits every point in your scatter plot. And as you start to have 1 or 2 or 3 or 4 points that can't hit the line, that are just a little bit off the line, well, now your correlation's 0.98, it's 0.95, it's 0.92. The more points that are off that line, the more it starts to move away from that perfect relationship, the more it moves away from 1. Of course, similar with -1. If you could draw a negatively sloping line that hits every point, well, now you have a correlation of -1. Another fact about correlation is that it's the same regardless of which variable is your explanatory variable and which is your response variable. Switching your X and Y does not in any way change your correlation. And then one final fun fact while we're riffing off the F's. The value of R does not change when either variable is converted to different units, right? So I think we implied that we measured height in inches and weight in pounds. If we changed inches to feet or even to something like centimeters, if we changed pounds to grams or stones or some other measurement of weight, the correlation is going to stay the same. That's a pretty nice property, actually, right? Changing those units doesn't actually change the correlation, and that makes sense, right? It would be weird, wouldn't it? It would be weird, like if we measure this biological relationship between height and weight for like Americans, and we get one correlation, and then we ship them over to England where they measure the same people using a different metric system, and the correlation, the sort of biological relationship between height and weight has somehow changed. That would be weird. So it's a very desirable property, the one that we're looking at now, and it's something that correlation possesses. There's the formula for it. It's a little bit of a doozy. We're never going to calculate it by hand. I'll actually show you how to use SAS to calculate it in just a slide or two. It's still kind of worth thinking about a little bit, though. So what's going on there, right? We have 1 over n minus 1. N minus 1, or n, is the size of our sample. It's referred to as our sample size. That kind of weird looking thing looks like the letter M that someone like cow-tipped. Or I guess looks like the E, right? That's the Greek letter capital sigma. That's the add it all up symbol in math, right? Normally there should be like some subscript saying like I equals 1 to n, but I got a little lazy with my typesetting. But what that's saying is sum up all the observations, and for every observation, right, do that process in the parentheses. So for every observation, basically look at its y variable, subtract y bar, the sample mean of y. Look at the x variable, subtract from it x bar, the sample mean of x. Divide by sy, that's the standard deviation of y. Divide by, right, sx, that's the standard deviation of x. Do that for every observation and add up those results. I sometimes joke in class. I say like, "Oh, of course, that's exactly what." If I just asked you to guess the formula for correlation, I'm sure that's what you would have come up with. And people laugh because it's like if you look at it, it does look crazy, but there really actually is some intuition, right? All the magic's happening upstairs, right? All the magic's happening in that numerator. The y minus y bar, the x minus x bar. Let's think about it. Why can we intuitively see like why this formula will spit out a positive number, a number between 0 and 1? Can we see why this formula is actually pretty cleverly constructed in such a way that it will give us a positive number if there's a positive relationship? Well, let's think about it. So a positive relationship means what? If x is large, y tends to be large. If x is small, y tends to be small. So let's look at either one of these cases. What if x is large? If x is large, what does large even mean? Large is a relative term. A lot of adjectives are relative terms, right? Large just means larger than average. What's kind of implied when we say that, right? So if someone's large, then x minus x bar is going to be positive, right? They're 6 feet, maybe average height's 5 feet, so 6 minus 5 is 1. Now, if it's a positive relationship, x being large, we expect y to be large. So y minus y bar is positive. We multiply two positive numbers, we have something that's positive. Standard deviations are always non-negative, so they're not going to change the sign. So that's a positive number. You might say, okay, well, what if the observation is small? Well, if x is small, it's a short person. Well, 3 minus 5 is negative 2. So now x minus x bar is negative. That doesn't sound good. But if x is small, we expect y to be small. And if y is small, then y minus y bar is also negative. That doesn't sound good, except what the kata. I have a PhD in statistics. I have a master's degree in math. I still don't exactly understand the magic behind this, but if you multiply a negative number times a negative number, wow, now it's positive. And in our case, it just saved the day, right? No matter what happens, whether x is small or whether x is large, we expect, right, the product of those terms to end up being positive. And so we're essentially adding up a bunch of positive numbers, and that's why our correlation is positive. Kind of cool, right? Why don't you try to reproduce the logic I used and show yourself, show your significant other, small children, older parents, how that logic would work in the situation of a negative relationship, how that's going to give us a negative number, how this formula, if we have a negative relationship between x and y, show us why this formula is going to give us a negative number. Why don't you maybe pause this video, maybe do that. Why don't you give yourself maybe a break? Although we're actually getting pretty close to what I would suggest as a breaking point. So I don't know, maybe do it and tough it out for a few more slides. So it's always easier in the classroom. You can kind of juxtapose like this thing with like the other slide. The way we're doing it now, I can only show you one slide at a time, so you're going to have to pause and go back. Maybe actually, to be honest, what I always recommend that you do, and I guess I'll say it now. I recommend that you print the PowerPoints. I post the PowerPoints on D2L. I would recommend you print them. You have them handy, right? Those are, you can go back and forth. You could take notes on them right there in front of you. I'd have like a paper version in front of you, and then you're like listening to this video on YouTube. So an example like this, we're at the video, I have this kind of multiple choice question for us. The multiple choice question is referring back to our scatter plot of height and weight, which is a few slides back. Of course, if you had your papers printed, you could just kind of pull that graph up. You probably could remember roughly what it looks like. Based on that scatter plot, what would you expect the correlation to be? Multiple choice. Do you expect it to be 0.8, 0.2, 0, negative 0.2, negative 0.8? I could add 1.5, negative 1.5, but I know you wouldn't fall for it, right? Correlation's always between 1 and minus 1. So if you go back to that scatter plot and you look, you'll see an upward trend, right? It's a positive relationship that we observe between height and weight. So we could rule out D and E. It's not negative. And there is a linear relationship, so we could rule out 0, which would imply no linear relationship. So now we're stuck between 0.8 and 0.2, which is basically what? Something close to 1, indicating a strong relationship, or something close to 0, indicating a weak relationship. In our situation, I think with like one exception, most of the points look pretty close to a line. So I would call that a stronger relationship. So, right, I would expect a 0.8 over a 0.2. I would expect you to be able to look at a scatter plot and do a multiple choice like this. Now, I mean, if I asked you to pick between like 0.8 and 0.7, that would not be a fair question. Right? You can't look at a scatter plot and say, oh, that's 0.85 or that's 0.84. But you definitely can look at it and say, this is closer to 1 than it is to 0. Or, right, 0.8 is probably a more reasonable estimate than 0.2. That is something I would expect you to be able to do by looking at a scatter plot. Oh, yeah, here we are, right? So we look at that and right, see that right with that one exception, if you look up, there's like a point at like what is that? Like 69, 200. There's a kind of outlier up there, but all the other ones actually are very, very close. Looks like we could draw a line that would come close to hitting all of the rest of the points. And that line's going up, so we would call that a strong positive linear relationship. Keep your eye on that 69 200. So something about them seems a little bit off, maybe a little bit shady. I don't know. So how could we verify our guess? Well, you could crunch out that formula. Not very fun. You could multiply, divide, add a bunch of numbers, or write a little bit more practically. We could use proc core, right? So in SAS, there's proc core. Core is in correlation. There's a var statement. You see var statements a lot in procs. And you can actually specify any number of variables in there. So if you put like 5 variables, proc core will give you the correlation for all possible pairs of those 5 variables. In our example, we just have 2, height and weight. So I put those in, and lo and behold, I don't show you the output. You could try it yourself, but it ends up being just about 0.80, right, as we had suspected. Now, question: are correlations 0.80? Ah, man, I hate it when this happens. It's kind of heartbreaking as a teacher. We take our first test. Everyone did great. I love that. That makes me happy. But unfortunately, after an extensive statistical audit, it was determined that the 200-pound individual, I hate to say it, that they got caught. They got caught cheating. Yeah, it's not a joke. It gets you in a lot of trouble. So I don't know what happens. What happens if you're a 200-pound well, what happens if you're a 200-pound individual who cheats? I guess the weight has nothing to do with it. What happens in this case? If you cheat, you go away, right? You vanish, you're gone. You're not in our data set anymore. Where does the person go? I don't know. Maybe Siberia, maybe Narnia, maybe Jersey, but right, the person's gone. They're not in our data set anymore. So let's go ahead and look. Right, there it is. Right, that point that I'm talking about. Imagine if that point wasn't there. How would that change the correlation? So with that point there, it's 0.8. If that point goes away, is the correlation going to change? Yes or no? If you think it's going to change, is it going to go up or down? Or maybe turn negative? Do you think it'll go from 0.8 to 0.9? 0.8 to 0.7? Why don't you write down on your piece of paper what you think is going to happen? Exactly. It's going to go up, right? And it turns out maybe go up by a lot more than we might expect, right? So we certainly should expect that, right? Without that point was sort of an outlier. So if we get rid of that outlier, we have an even stronger positive relationship. So a stronger positive relationship is one that's closer to 1. So we expect it to go up from 0.8. Maybe not so much to here. This is getting darn close to a perfect linear relationship. It seems a little surprising. You would think that maybe one person, one observation shouldn't have so much of an impact on the value that we're looking at. But the reality is, for better or for worse, that it does. That's because correlation is not a resistant measurement. A resistant measurement is a measurement that is not unduly influenced by extreme observations. We just saw that correlation is influenced by extreme observations, right? Whether or not you add that one extreme point can change the correlation by like 20%, right? It increased it from 0.8 to almost 1. That was a big swing, showing us that correlation is not resistant, a little bit of a flaw or limitation of the measurement. Now, a few wrap-up questions. What would the correlation be if we wanted to test whether or not a person's weight predicts their height? We just did a bunch of calculations for using height to predict weight. What about using weight to predict height? Well, as we mentioned in the previous slide, it's not going to change. Similarly, right, as we already said, if we measured weight in kilograms and height in meters, also the correlation remains unchanged. It would still be that 0.80 or the 0.98, depending on whether or not that student cheated. Now, a cautionary. A strong correlation does not always mean a cause and effect relationship. There's a lot of stories out there about like politicians, right? Mayors, business people, right? Making like you know, like civic policy, making business decisions based on the misunderstanding of this concept, right? The catchphrase that we might hear a lot, maybe I've already heard, right, is that that correlation is not causation. Correlation is not causation. Here's an example. I looked at the data once. In the Philadelphia area. Every year, so I had like data for every year, and I looked at like how much had been like donated to charity, like you know the dollar value of everything that had been donated to charity, and the amount of crime. And so like I had it like maybe like in like the year like 1920, you know, it was $10 were donated and crime was 3, and then 1921, now there was $12 of donations and crime was 4. And the next year there was $13 of donations and crime was 5. Right, those aren't the real numbers. I'd have to dig them up, but right, it turned out that there was like a pretty strong like positive association. Correlation was like about 0.78. That's actually kind of cool, isn't it? I don't know. You may or may not be interested in sociology. My undergraduate degree, true story, is criminal justice, right? For a very, very, very brief period of time, I served as a as a police officer. Yeah, Radnor Township. I was a police officer there for, I don't know, roughly 2 weeks or so. So I'm interested in sociology. I'm interested in crime. And like, I mean, I've always wanted to be a crime fighter. I was reading comics from like a very early age. So what do we see as statisticians? How can we use our statistical expertise to fight crime? To help out the Batmans, the Supermans, the Wonder Womans of the world? Well, we have the answer right here, right? Because what does 0.78 mean? It means a strong positive linear relationship. It means, right, as one goes up, the other goes up. Or, right, what also could it mean? It means as one goes down, the other goes down, right? As the amount of charitable donations goes down, the amount of crime goes down as well, right? So that means that if we wanted to eradicate crime, all we would have to do is make a pact as a class, as a university, as a society, to be as miserly as possible, right? As stingy as possible, and save the world. Yeah. Oh man, it's that time of year. I'm creating this thing. It's actually I can't see the date. It's not showing on my computer right now, but I don't know, 21st or something like that. It's a Monday and Christmas is on a Friday, so I'll leave that math for you. Oh, the thing that gets me so mad. Do you ever see those people? I don't know if they're doing it this year, but like they're like in the Target parking lot and they're like wearing like a Santa Claus hat and they're like ringing a bell and they're like, "Oh, why don't you give to charity?" Oh, I hate those people. When I see them in the parking lot, I spit in their face. Like I go crime monger. Like what are you doing? Like contributing to the downfall of society. Oh, it makes my blood boil. Yeah, so something feels wrong, right? We probably shouldn't be spitting in people's faces. Certainly not people that are gathering money for charity. But how do we reconcile that? I lied about analyzing the data, but I am pretty confident that it would be maybe not quite as strong as 0.78, but it would be positive. Why? Why would it be positive, right? Well, there's other factors, right? And maybe one of those other factors is like population growth, right? Maybe this third variable, this lurking variable is like population, right? I said I gather this data every year. But in general in the Philadelphia area, right, every year there's more people. So when there's more people, well, there's the good and the bad. People have both, right? People are complex creatures. So, right, more people in the Philadelphia region means that there's more stuff being donated to charity. That's good, but it also means there's more crime. That's bad. So we see them growing together. That sounds like a positive relationship, but it's not that one of them is driving the other. It's that sort of both of them are being driven by this third variable, which is population growth, right? Correlation does not imply causation. And I know that my example seems really extreme and silly, but there are plenty of examples of actual politicians making policy decisions based upon the same kind of silly, naive understanding, right? If you want to read some of these examples, Freakonomics is a pretty good book and podcast for kind of coming up with like some good examples or seeing some good examples of how, right, this is, I don't want to say misused, but like misunderstood, and how those misunderstandings lead to bad decisions. Yeah, so we must be cautious. We must be cautious even when a correlation is strong in concluding that the explanatory variable causes the response variable. Sometimes that behavior is related by some third or fourth or fifth lurking variable. Now, in terms of causality versus association, that's what we call it. If it's not causality, we say correlation is a measurement of association. Um, Most statistical procedures in our course look at association, not causation. Causation is demonstrated through experimental design and qualitative judgment. So there's a really, really great write-up on this distinction in our textbook. I'm going to leave it to you to read it because I would just basically plagiarize it word for word. It's so perfectly and succinctly written that I can't say it any better or any more tersely. So I'll leave it to you to read that little snippet on your own. I really encourage you to do, because it is an important distinction to be aware of. Again, it's being aware of the limitations of the still very powerful techniques we're going to learn in this class. But we don't want to overstate their power either. So one last warning, and it maybe should be something we're kind of already kind of comfortable with, and that is we need to always be cognizant. It's kind of easy to fall into this pit that a correlation of 0 doesn't necessarily mean that there's no relationship. It just means there's no linear relationship. And that's why the scatter plot is an important first step, right? The correlation in some ways feels like more descriptive, more precise. And it often is, like, at the end of the day, kind of like the sort of punchline of our analysis. And so it might be tempting to just jump straight to the correlation, but we do instead want to start with the plot. Why? Well, let's take a look. Imagine we want to look at the relationship between X, the amount of time spent studying for an exam, and Y, the grade on the exam. This example is, I don't know, maybe a little bit tongue in cheek. Um, I don't see it so much in my graduate classes, but in my undergraduate classes, I do see it. Like occasionally, like I'll be given a big test in like an undergraduate class, and like a student will kind of show up, and their eyes are kind of like wild and like feral and like bloodshot, and they're like double fisting like a Monster Energy drink and another Monster Energy drink, a two-headed monster, and they're all like wound up and they're like shaking, and they're like, I was up all night studying, and they're so excited, and I'm just like, oh no, it's not going to be good, right? I, I so I always in those situations like to imagine a graph like this, right? That I mean, certainly I think we buy into like some studying's better than none. Most people feel like it's maybe the best way to do well on a test is to study for the test. So it would make sense to see a positive relationship like we're seeing on the left part of this graph. The more we study, the higher we expect our test score to be. And actually, I mean that the fact that it kind of starts to flatten out, I mean that makes sense, right? I mean there certainly is diminishing returns. I don't think any of us would argue that. I mean, you read the chapter once, that's probably great. You read it a second time, hey, you kind of found a few things you missed the first time. It helps, but probably reading a third, a fourth, a fifth time, you're not really gaining very much. Right? And in the exaggerated sense, if you keep reading it, 10, 20, 30, 40, 50 times. Well, now you're like, that time you're reading is like time you could have spent sleeping, that you could have spent resting, that you could have spent doing other things, right? And now you're showing up with no extra knowledge but less sleep, and so, right, because of the lack of sleep, now you're seeing your score go down. I don't know. That part may or may not be realistic, but right, certainly a graph like this, the important point is that a graph like this would have a correlation close to zero, right? Why? Because like half the graph is upward sloping, half the graph is downward sloping, and it turns out sort of mathematically like those two halves sort of cancel each other out. So I mean, there definitely is a relationship here, agree? Like a very interesting relationship is clearly observed from the scatter plot. But if we just instead just jumped straight to the correlation, we might see that the correlation is zero and mistakenly conclude that there's nothing going on, when of course that's not the case. A correlation of zero just means there's no linear relationship. And because there's no linear relationship, it could just mean that it's just like random scatter, and there is sort of, quote, nothing going on, but it could also mean that there's a more complicated relationship, like this kind of like this quadratic curve we're looking at right here. Okay, so that kind of wraps up like the first half of this week's lecture. If you haven't already, I would encourage you to take a little breather, stretch your legs, use the restroom, get a snack. It's the beauty of narrating these things. I actually think I'm going to take a nice long nap and then come back and finish narrating the second half of this thing. So it's a good breaking point. I'd encourage you to do it, and then this video will still be waiting for you when you come back. So I'll talk with you then. All right, so first half of this lecture, right? First half of this lecture, we talked primarily about this idea of bivariate relationships. We said, okay, the way to explore, the sort of first step to exploring a bivariate relationship is to start with a scatter plot. If we do a scatter plot and we see what looks like it might be a linear relationship, then it makes sense to calculate the correlation. The correlation's a numerical measurement between -1 and 1 that measures the strength and direction of that linear relationship that we observed in the scatter plot. So the focus was really on scatter plots and correlation. We're getting ready to, in the sort of second half of this lecture, we're getting ready to segue to something called linear regression. In particular, this week we're going to talk about something that's called, it's often called simple linear regression, bivariate linear regression, where we're only dealing with two variables, right? Two variables, x and y. When you add a third or a fourth or a fifth variable, which is certainly something we'll do, I think we do it maybe in the third week of the class. That's called multivariate regression. So, right, what were we talking about? We were talking about correlation, right? We made the observation that if the absolute value of the correlation is close to 1, right? That means that correlation itself is close to 1 or minus 1. Then that means that there's a strong linear relationship between x, the explanatory variable, and y, the response variable. So making that statement sort of begets a curiosity. A curiosity leads to a question. If we think that this is a linear relationship, right? If we think the scatter plot approximates a line, what is this line, right? Of all the infinite lines, we know a lot about lines, right? We know a lot about lines from our math class, right? Of all the infinite lines that could be drawn, what is, and is there even, a one best line that fits that scatter plot better than any other line, right? What is the sort of true linear relationship between x and y? Yeah, so the scatter plot approximates a straight line. The goal of what we're going to talk about now, the goal of linear regression, is to find, of all the lines, what is the one best line that fits this scatter plot better than any other line. One very common way of doing this is something called the least squares, using something called the least squares criterion. And according to this criterion, the best line sort of follows this process. Let's actually start with this process for any line. So imagine we draw a line through a scatter plot. And we look at the vertical distance between that point and the line, right? How close is a particular point to the line? And this idea of closeness is measured by its vertical distance. We look at how close a point is for the line for all of the points, and we square that vertical distance. We square it because why? Because it's a very common statistical trick. Some points are above the line. That means they have a positive distance. Some points will be below the line. That means they have a negative distance. And so if we actually just added up the distances, the positives and negatives would cancel. So to prevent that from happening, we look at the squared distances and we add those squared distances together. The least squares criterion gives us what's called the least squares regression line, LSRL. And the least squares regression line is the one that minimizes this criteria. That is, right, of all the lines where you kind of look at the sum of the squared vertical distances, right, the regression line that we're picking is the one that makes this sum as small as it could possibly be. Now, a little side note, we'll kind of talk more about this in future lectures. That vertical distance between a point and the line is referred to as its residual. An important term that we'll use a lot in this class and just in statistics in general. So there's our scatter plot. I used something in this case, I think I used SGplot to make this slightly nicer looking plot. I'll show you the syntax for it next week. But here's our scatter plot. I drew our line. Notice is actually, in this case, there's only 2 points above the line. It's because of that outlier, right? That outlier is sort of so far above the line that we kind of need a lot of points below it to kind of balance out. But that is our least squares regression line. It's the one that minimizes that least squares criterion. One nice thing about the least squares criterion, it's kind of cool math fact that you can prove mathematically. It's not intuitive, but it's kind of remarkable that for any scatter plot, no matter how crazy, if you use the least squares criterion, there is always one unique line. That's the part that to me is a little surprising. For any scatter plot, no matter how crazy, there's always exactly one unique line that will fit that scatter plot better than any other line using this particular criteria. Here's that idea about like the vertical distances. So again, like for every point I drew a line between that point and the line, right? And that shows us essentially how far the point is from the line. So we're looking at, right, all the distance between the point and the line. We want that distance to be small, but we want it to be small for all the points. So we got to kind of look at this aggregate distance. And so because, right, some points are above and below, that is we have positive and negative distances, we square all these distances and add that up. And the least squares regression line, the one that's actually on this slide, is the one that makes that as small as possible. It's the one that fits the scatter plot as best as possible, right, given this criteria. So, again, maybe based on a scatter plot, maybe based on some previous research, maybe based on a hunch, we have two variables, x and y. We conjecture that there is this sort of true kind of platonic linear relationship between the two variables, right? That's kind of like the underlying reality that we would like a glimpse into, that we would like to explore. This theorized relationship, right? This linear relationship is often written the way we wrote it right here. So those kind of funny looking B's, those are the Greek letters beta. And I have some subscripts, right? So it's convention to call that first one beta naught and the second one beta 1. So we have this linear equation, y equals beta naught plus beta 1x. That's no different. I mean, what did we maybe learn in like grade school? In grade school, we called it y equals mx plus b. But it's the same equation, agreed? Just instead of m and b, we use beta naught, beta 1, right? We use beta naught because there's 0 x's sort of associated with that number, with that value, and beta 1, right, is the first, is sort of like the coefficient for our number one variable. You might imagine, so we might almost write that as like y equals beta naught beta 1x1. You could already imagine, like, if we had a second variable, it's going to be plus beta 2x2 plus beta 3x3 and so on. But right now we're only focusing on simple linear regression, just 1y and 1x, and that's what this linear relationship looks like. Now, of course, unless you're God, you don't know that relationship. You'll never know that actual relationship unless you're whoever it is that built the universe. Right? These are like the universal laws that we're trying to inquire into. We can't know that information without say sampling the entire world, sampling the entire population, which is generally infeasible. So what do? Just like we always do in statistics, we settle. We can't look at the whole population, so we take a sample. That sample is essentially what's being shown in our scatter plot. We look at the sample, we look at the scatter plot, we create this best line that fits our sampled data, our scatter plot as best as possible, and this becomes our best guess for the hypothesized linear relationship, right? So we have the sort of true linear relationship, right? This idea of universal truth. We do some experiments. We take a sample. Based on our experiments, based on our sample, based on our data, we come up with our best guess for what we think that linear relationship might be. And that best guess is written as y hat equals beta naught hat plus beta 1 hat x, right? The beta naught hat is our best guess for beta naught. That beta 1 hat is our best guess for the true but unknown beta 1. And we tend to also put a hat over the y to just show that this is kind of like our estimated equation, or as we'll see, we sometimes call it our prediction equation. So we generate this line. What do we do with it? Well, one very powerful use that we'll kind of illustrate over the course of the class is sometimes we can get a lot of information just interpreting the slope. That is, sometimes just the slope alone has a nice interpretation. We'll actually see an example of this. We'll see an example of this down the road in just a little bit. And occasionally, certainly less often, but on some occasions, the y-intercept also has a nice interpretation and might give us some insight into whatever problem it is that we're studying. We can also use our regression equation to make predictions of y for given values of x, right? That's maybe one of the more common, more powerful uses, and that's why, as I implied just a moment ago, we sometimes call this regression equation, we sometimes call it a prediction equation. So let's start with this, right? The slope of a line. The slope of a line, right? This should be intuitive to us. The slope of a line has the same sign as the correlation, right? So, right, if we have a positive correlation, that means our regression line has a positive slope. If we have a negative correlation, that means our regression line is a negative slope. It can be interpreted as the rate of change of the response variable as the explanatory variable changes, right? It tells us how many units we expect y to change for each unit change of x, right? That's, again, in math, we talk a lot about this idea of rate of change, delta y over delta x, right? That's just describing ideas of slope and rate of change. Slope is a rate of change. Now notice, right, I bolded the word expect because, again, we want to avoid mathematical interpretations of, we want to avoid mathematical interpretations of slope that miscommunicate a level of determinism, a level of certainty that is just simply not present in whatever real life phenomenon we're trying to study with the application of statistics. The y-intercept tells us the value. Again, we're using probabilistic language, not deterministic language. It tells us the value we expect the response variable, that we expect y to be when x, the explanatory variable, is 0. We'll see in a lot of cases this is not necessarily a useful interpretation because in a lot of cases, it doesn't make sense for x to be 0. Also, in a lot of cases, x being 0 is what we would refer to as an extrapolation. We'll more formally define interpolation and extrapolation down the road next week, I believe. But for now, at least, certainly it should make sense that in a lot of situations, just x being 0 doesn't make sense. And so because of that, right, we get a y-intercept that's a little bit nonsensical. So there certainly are examples. I'll mention one or two down the road where this maybe would have like a nice interpretation, but probably more often than not, it doesn't. That's still not to say it's not important, right? It is important mathematically because, right, the y-intercept is kind of, we could think of it as if nothing else, as like the anchor of our line, right? Of all the infinite parallel lines of a particular slope, the y-intercept says which one of these, right, specifically fits the scatter plot the best out of all of them, right? We sort of nail down the right slope, but there's still an infinite number of lines with that slope. So the y-intercept is what we need to make that line unique. And just as mentioned before, these interpretations, the interpretation of slope, the interpretation of y-intercept, are often useful in and on their own, right. Let's look at this kind of interpretation and kind of what it adds to the picture in the context of two examples. So let's say that x is the amount of time that a student spends studying on their exam. Let's say y is the grade they get on that exam. And let's say that we gather the data, we plot it on a scatter plot, and we fit the regression line, and we see that the slope of this line is 10. So like maybe imagine like a real steep looking line. And we find the correlation's 0.9, so strong positive linear relationship. Right, all the points are kind of packed tightly around that line of slope 10. Now, how would we interpret that slope? We would interpret the slope as saying that for every 1 unit of x, right? So in this case, for every extra hour that we spend studying, we expect y, our test grade, to increase by 10. In this case, our units are percentage points, so by 10%, or right, increase by 10 points. Very similar example, right? Still same variables, amount of time that a student spends studying, grade on their exam. Correlation still 0.90, but now the slope of the regression line is found to be 0.10. So imagine now that our line is very, very flat looking, right? We would interpret that as saying that for every 1 hour we spend studying, we expect our test grade to increase by 0.10 points. Right? So that's basically saying for every 10 hours we study, we expect to go up by 1 point, or maybe like 1 percentage point, which means that if we wanted to go from an A to a B, we'd have to study, or go from B to an A, sorry, we'd have to study 100 hours, right? That's a lot, isn't it? And so simple examples, but I think they show us a couple different things, right? They show us that correlation is not the whole story, right? Example 1, example 2, both had the same correlation, but very different situations. How do they differ? They differ in terms of their slopes. And the slopes dictated, right, how we might take action, right? That's like the ideal application of statistics, is it guides us in terms of making a decision. And the first example, we feel strongly motivated to study, right? The way that test is constructed, it's maybe, I would say, well constructed in a way that it rewards studying. Maybe a little too much. For every 1 hour you spend studying, you can expect to go up an entire letter grade. So I would definitely study for that test. On the flip side, you have this test right here that almost seems like study proof. For every 1 hour you study, you go up like 1/10 of a point. That's crazy. 10 hours is a long time for 1 percentage point on a test. And so probably in example 2, we're probably inclined not to study, right? The slope delivers extra information and important information. Right? In both situations, the correlation is 0.90. But what is the correlation telling us? The correlation is telling us a strong positive linear relationship. What does a positive relationship tell us? A positive relationship tells us as x increases, we expect y to increase, right? But the natural follow-up question to that is, by how much do we expect y to increase? And that is the answer. That is the question that the slope answers, right? the slope provides that extra information. So, right, we also said the second big use of these regression equations is to do prediction, right? We can predict a value of y for a given value of x. Real easy to do. We just take our equation and we plug that value of x, whatever value of x we want to predict for, we plug that value into the regression equation. So, I mean, lots of different examples of where prediction might be useful. I like to keep like my actual like the examples I do a lot of working with. I try to keep them simple, right? Because I mean, we're doing a lot of learning just in terms of the statistical concepts. We don't need to add to that burden with like a kind of crazy problem. But sometimes when I do it that way, we lose sight. We think like statistics is only useful in these kind of silly examples, and that's of course absolutely not the case. Right? So I mean, here are some real life examples, right? We could use the average weekly temperature on a given week to predict like the demand of natural gas, right? So if you're Pico, you're not manufacturing. You don't like drill your own mountains. You're not manufacturing your gas. You're ordering it from someone. So Pico wants to order gas to have enough to supply the Philadelphia area, right? Because if it's a cold day and we turn on our heater and nothing happens, right? It's consequences. Customer outrage and maybe worse. So it's in Pico's strongest interest to make sure they have enough gas every week. On the flip side, they'd prefer not to order too much gas, right? Ordering too much gas is going to lead to storage issues, to inventory costs, and it means they spent money that they didn't need to, that they could have perhaps just invested in other ways and made a return on that investment. So, right, Pico is strongly motivated as a company to find that sweet spot, to get as close as possible to the exact amount of gas that they're going to need next week. Now, of course, they don't have a crystal ball, but what they do have is this sort of universal fact, and that is that there is a very, very strong relationship between temperature and gas consumption. If we're looking at cold winter months, right, then it would be a negative relationship. Does that make sense? Might be our first example of a negative relationship. We could think of it as this way, like as that X, as the temperature is going down, it's getting colder. That means we're turning our heaters on more, which means that, right, that gas consumption we would expect to go up. So as a negative relationship, possibly linear, and right, we could fit that line, and we could use that line to predict. Now, of course, the really nice part is what? That, I mean, it's certainly not perfectly predictable, but temperature is somewhat predictable, right? We can go on weather.com. I'm sure Pico uses something more sophisticated than that. We can get a good guess for what like the average temperature is going to look like next week. I mean, you and I could do it right now with Google AccuWeather, and then they could plug that into the equation and predict what the demand of natural gas is going to be. Pretty cool. Another example, this one also probably a negative relationship. X is the miles driven on a certain tire, and Y is its tread depth, right? So your tires have these kind of these little grooves in them. The grooves are called its tread. And right, the more and more and more you drive on that tire, right, it wears that tread away. It's what we start talking about, like, oh, it's a bald tire. It means the tread has been like worn completely away. There's no more grooves. It's now smooth. And that's when you're supposed to replace your tire, right? So, I mean, realistically, like these safety warnings are like the tread depth gets to like a certain depth, right? Normally, like a fresh tread depth, say, is maybe 1 centimeter. it's too large, but let's just go with it. Maybe when it wears itself away to 1/2 centimeter, that's when you're supposed to replace your tire. But like realistically, like you and I aren't going to go out on a cold winter day with like a tiny magnifying glass and a tiny ruler and like get under our car and kind of squint, might need a tiny flashlight, and try to measure that tread depth to see if we're at 1/2 centimeter yet. It's dirty down there. But we don't have to. Why? Because of the power of statistics, right? It turns out that there's an incredibly strong negative relationship. Like the correlation for like one of the studies I saw was like 0.974, negative 0.974, negative 0.98, right? That is, it's almost like a perfect prediction in terms of the amount of miles that you drive on a tire and what its tread depth is. So what that means is you can kind of work backwards using this prediction equation, right? You can create this equation. You could plug 0.5 in for y. That's that sort of danger zone, 1/2 centimeter, and try to solve for that value of x, the number of miles driven that you expect to be associated with 1/2 centimeter of tread depth. And then, of course, you can tell people when they buy your tire, instead of telling people replace it when the tread depth is at 1/2 centimeter, you can exploit this statistical relationship and say, when you drive 10,000 miles, make sure you replace it. And of course, what they know behind the scenes that aren't telling us is at 10,000 miles, that's when the tread depth is expected to be at 1/2 centimeter. And that's why you should be replacing it then. Pretty cool, right? Incidentally, the second bullet point is also an example of when the y-intercept might have like a nice interpretation, right? So the y-intercept of this equation would be what? It would be the value that we expect y to be when x is 0. So in that case, it would be what? It would be like the expected tread depth of like a brand new tire. And then we can look at the slope. It's going to be a negative slope because the fact that it's a negative correlation. We can almost look at that slope as like an erosion factor, right? So maybe our miles are in units of thousands. So maybe our slope is like negative 0.1, which would basically be saying what? It would be saying like for every 1,000 miles you drive, you expect that tread depth to erode by like 0.1 centimeters. Pretty useful, right? Yeah, next time you don't have to get down on your hands and knees under your car with a tiny ruler, you can thank statistics. Third bullet point. Yeah, little gross. Sometimes, I mean, statistics isn't scared to go there. Let's let X be the amount of parasitic eggs in a horse's fecal movement, and let's let Y be the amount of parasites in the horse's stomach, right? So my PhD's from the University of Kentucky, horse country, and I did a lot of statistical consulting there. And did a lot of consulting and projects for veterinary science, who did a lot of horse studies. And this was like things like this were kind of like a big deal, right? So a horse gets parasites, worms or whatever it may be, and that's bad. You want to give the horse medicine, but the concentration of that medicine ideally should be tailored to like the amount of parasites in there. Making it too strong is like bad for the horse, makes it sick and does other things. But making it not strong enough means you don't even kill the parasites, and it was just sort of a wasted experience. But you can't know the number of parasites in a horse's stomach without cutting it open and looking in the stomach, and of course that kind of defeats the purpose. So what do you do instead? Well, right, you get the horse's bowel movement, right? You have some poor unlucky graduate student. I don't know who's doing this. It wasn't me, thankfully. Going through the fecal matter, and I guess there we are with that tiny magnifying glass and tiny ruler, looking and counting parasitic eggs. And as we might expect, right, there's a strong relationship between these. What do you think for the third bullet point? You think it's a positive relationship or a negative relationship? Exactly. Good job. You're really catching on fast. This would probably be an example of a positive relationship. All right, so that's well and good. But like, how do we do it? in particular, I keep talking about we have the scatter plot, and we have this criteria that comes up with this best line. But like, how would I do that mathematically? And so I guess I should say a couple things. There are formulas. The formulas are in our textbook. You can Google them. They're a little bit crazy. I certainly would never wish, even on my worst enemy, doing those calculations by hand. Certainly, even for like a modern day data set with thousands and thousands of observations. And that's fine, right? Because we have software programs, something like SAS, to do the heavy lifting for us. So realistically, right, how do we get like this equation of best fit? We ask SAS to do it for us. For those of you that are equation files, feel free to look it up in our textbook. So here we are, right? Here's our SAS. There's our data set. And we want to create the regression equation. We do that. We'll see lots of procs that do it. Probably the most specialized and most basic is called proc reg, right? Reg is in regression. Proc reg uses a model statement. The model statement is like the heart of most statistical modeling procedures. There's a lot of statistical modeling procedures. Most of them use the model statement. And it works in the sort of same way. You put the y variable on the left, you put an equal sign, you put the x variable on the right. Or variables, as we'll see in future lectures. And here's our output. A lot of numbers there. For now, we're actually only going to focus on 2 of them, but I promise by the end of week 3, you'll know what all of these numbers mean. For now, we're going to go to that bottom parameter estimate section. And it has a column that says parameter estimate. It's got a negative 190.53854. It's got a 4.95553. It says intercept for the top one, right? That's our y-intercept. It says height for the other one, right? That's our slope, the slope for the variable height. So those are our parameter estimates. So what are we going to do? What we're going to do is we're going to get our piece of paper, we're going to get our pen, we're going to get our pencil, and we're going to write down what that equation looks like. Go ahead, pause it, and take some time. All right, let's see how you did. There's the equation, right? The equation of our least squares regression line is negative 190.54. That was the y-intercept. Plus 4.96, that was the slope. Did a little bit of rounding in both those cases. 4.96 times x. Let's interpret. So beta 1 hat, the estimated slope, our best guess for the sort of true but unknown linear relationship between height and weight is 4.96, which says that for every 1 inch increase in height, we expect the weight of a student to increase by 4.96 pounds. Beta naught hat is negative 190.54. If a student had a height of 0, right? Not a very sensible thing. I don't know. Maybe we're talking about imaginary friends, imaginary students. Then we would expect their weight to be negative 190.54 pounds. Of course, it doesn't make sense to have negative weight, and that we're getting that sort of insensible answer because it also doesn't make sense for someone to be 0 inches tall. Right? In this particular example, the y-intercept does not really provide any kind of insight to the actual sort of biological mechanism that we're studying. Say that we wanted to predict the weight of a 70-inch student. Well, pretty easy. All we would do is take that 70, plug it into the equation. Do that, plug it into a calculator, we get 156.66 pounds. Yeah, pretty cool, right? Pretty straightforward, but as we'll see, Very powerful. Now, where do we go from here? Well, even though our best guess for the weight of a 70-inch student is 156.66 pounds, we would probably be quite surprised if the student exactly dead on weighed 156.66 pounds and not a bit more and not a bit less. Agreed? It would be surprising if it was exactly that, right? When we say that, we're probably kind of like thinking to ourselves that there's like this implication sort of close to that, right? It would also, of course, be surprising, and of course we know false, if to say that every 70-inch student in the entire world weighs exactly 156.66 pounds. That is, right, hopefully, right, our equation works well. Hopefully, the student's actual weight is sort of very close to our guess of 156.66 pounds, but we'd be surprised if it's exactly that. That implies what? It implies that we expect there to be error in this equation. And that's something that we haven't really taken into account or discussed yet. But it's the cornerstone for how statistics gets involved in this process. Right? That is, we should expect some error in our equation. As such, we need to adjust our earlier formula to explicitly model this error. And so there we are, right? This is the theoretical equation we had before, but more true to real life, right? The equation that we had before was deterministic. Few interesting world life phenomenons are deterministic. So what do we have here, right? Why? The weight of a student here, I added the subscript. So the weight of the ith student, right? This is just like an index because we have 100 students. So right, I could put y1, y2, y3, which is basically saying we're talking about the first student, the second student, the third student, right? We have this y sub I is beta naught plus beta 1 x1. So that the weight of that ith student depends on the height of the ith student. It's related in this linear way, but we do not expect it to be a perfect prediction. That is, we expect some error, and that's that third term that we add to our model, capital E as in capital error. Now, the errors, we have to attach some set of assumptions to sort of how they behave. These are the assumptions of linear regression. How well, right, our statistic methodology is going to work depends heavily on how well these assumptions are satisfied. For the time being, we're going to state them. We're going to learn them, and we're going to love them. We're going to just say, I hope they work because I know this process, or I hope the assumptions are true because I know this process won't work well if they're not. Towards the second half of the class, we'll begin talking about how we might be able to test these assumptions to give ourselves peace of mind that they hold, or to detect that they don't, in which case we'll talk about the workarounds or the solutions that we need to implement. So here are the errors. We conceptualize them as random variables, right? So if you took Stat 505, you're well acquainted with random variables. If you didn't, right, you could do a little bit of Googling. I do expect you to know what a random variable is. Random variables are actually discussed in a basic introductory undergraduate general education statistics class, right? A random variable is just some random phenomenon that has a numerical outcome. Random variables typically have three characteristics associated with them. They have a probability distribution. The probability distribution tells us, right, the values it takes and how frequently or how often it takes those values. A random variable has a mean, and a random variable has a variance, right? So those are the three questions that we want to be asking ourselves about this random error. What's its distribution? What's its mean? And what's its variance? All right, so here we are, assumption one. Our errors have a mean of 0. That is, sometimes the error is positive, which is basically saying that the observation is more than it should be based on the linear relationship. Person weighs more than they should based on their height. Sometimes the errors are negative. That is, a person weighs less than they should based on their height. But on average, these errors cancel out. On average, our linear equation correctly works. Right? That it's a little confusing to have two e's floating around, but right, as we remember from 505, that first e just stands for expectation. Expectation is a term commonly used for the mean of a random variable. Sometimes we call the mean of a random variable its true mean. It's different than the sample mean. Here's the true variance, right? The variance of a random variable. You can almost think of it as maybe like the population. Well, I take that back. Let's think of it as the variance of a random variable, or right, i.e., maybe the true variance. Is sigma squared. The variance of any error term, the error term of the first student, second student, third student, is sigma squared for all observations I. That's called the homoscedasticity assumption, right? So assumption one was we have a mean of 0. Assumption two, our errors have a mean of 0. Assumption two is homoscedasticity, right? Which says that the variance is a common variance. It's the same. That's the homo part, right? It's the same for all elements of our sample, for all elements even in the population. For every I, right, it's the same variance. That variance does not have a subscript I. And since it doesn't depend upon the person, it's also saying that it doesn't depend upon their height. So what we're basically saying is the variance of the errors is constant. It's a constant variance assumption and does not depend upon X. And then third, right, every random variable, what did I say it has? Every random variable has a probability distribution, a mean, and a variance. So, right, this is the third piece. What's its probability distribution? The common assumption is that it follows a normal distribution, which all of us, regardless of whether we've taken 505, should be familiar with. If you are not familiar with a normal distribution, that means you have not done the review material. You need to stop this PowerPoint, go back and do that. The errors follow a normal distribution. And then there's a fourth assumption. Right? I like to call it the 4th of July assumption, right? Because of Independence Day. And that 4th of July assumption is what? The 4th of July assumption is the independence assumption, that the errors are independent of one another. In 505, you talk about like a mathematical definition of what it means for two random variables to be independent of one another. That mathematical definition is what we're talking about, but understanding it's not too important for the level we're working at. I think most of us have a pretty good kind of like intuitive idea of like what it means when we're talking about independence, right? It means that if like the first person in our sample weighed more than we expected based on their height, that has nothing to do with whether or not the 100th person is going to weigh more or less than expected based on their height, right? That amount that they're off, that error between person 1 and person 100, or even person 1 and person 2 have nothing to do with one another, right? And that's often just a byproduct of like how you took your sample, right? If you took a nice, right, high quality random sample, simple random sample, we would probably expect the observations to be independent and the errors independent of one another. Down the road, we'll talk about the type of situation where this independence assumption might be violated and what that would look like. So another way of expressing all of this, right, compactly, is that the E sub I, right, the errors, are IID. You'll see that term, I think, a lot in Stat 506. IID means independent, identically distributed. They're independent. That's the 4th of July assumption. They're identically distributed. That means they're all the same. That capital N means normal distribution. A normal distribution is indexed by 2 parameters. Its mean, which we assume is 0, that was assumption 1, and its variance, which is sigma squared. Again, that variance doesn't depend on the I, so that variance is independent. The error as well. Both of them are independent of X. Yeah. So this is maybe a lot. This is certainly probably your basic introductory statistics class did a lot of what we talked about. You've probably seen correlation. You've probably seen simple linear regression. This is like the part of the lecture where we're moving away. You probably have not seen it discussed at this level, and like it's certainly not a general education statistics class, like a version of like Westchester Math 121. It takes some time to kind of develop an idea for kind of how these assumptions work, and we'll get there. All right, I'm always of the belief that you never learn anything the first time. It takes repeated exposure, and this is certainly one of those situations. I'm just exposing you right now. If it feels a little bit like I'm not sure what he's talking about, don't worry about it. It's okay. I'm going to keep coming at this, and eventually it's going to click. This is our first introduction. I want you to think about it. We'll keep talking about it. Yeah, there's no need to panic. We'll get there. Okay. So what we have now is this, right? We have 2 different equations, and those differences are important. We have the actual observation Y. That's like the actual weight of, right, that ith person, right? I grab a student at random, and I look at their weight. I put them on a scale and I weigh them. That's their Y sub I. We're conjecturing that that weight is this linear function of their height with this extra error term because, right, height doesn't predict weight perfectly. Right? Other factors go into it, right? Things like genetics, things like diet, things like how much we exercise, right? These are other things, lurking variables that affect our weight. Height alone isn't the whole thing. So that error term, that E sub I, is like encapsulating all this other stuff, right? It's encapsulating genetics and exercise and diet and all that other stuff is sort of in that error term, right? Based on height alone, we expect them to be, say, 200 pounds, but instead they're 190. Why? And the answer is, well, unique aspects, idiosyncratic aspects of diet and genetics and exercise and all that other stuff is why. So that's our sort of theoretical equation, the one that we would like to know, that we would like a glimpse into, but we will never know it perfectly, right? Unless we're the architect of the universe. Instead, we perform some experiments. Instead, we take a sample, and from that sample, from the data in our sample, we come up with the best guess for that equation. That's our Y sub hat, right? The Y sub hat, it's different than Y. Y is the actual weight. Y sub hat is what we predict it to be based on our information and based on our best guess for this equation. So that Y sub hat is beta naught hat plus beta 1 hat times x. Right? Again, beta naught is the unknown population intercept. In statistics, we call an attribute or characteristic of a population, we call that a parameter, right? P and P. A parameter, it's alliterative. A parameter is associated with a population. Beta naught hat is our best guess for the unknown population y-intercept. It's based off a statistic, or it's based off a sample, so we call it a statistic, right? So the other sort of definition for us that we should have had exposure to already is a statistic. A statistic is a number generated based off information in our sample. Also alliterative, S and S. Similarly, beta 1 is a parameter, beta 1 hat is a statistic. Beta 1 is our unknown population slope. Beta 1 hat is our best guess for that unknown population slope. We were probably first introduced to the idea of parameters in statistics in the context of mu. So that kind of U-looking thing is called the Greek letter mu, and x bar. Mu is the population mean. X bar is the sample mean. We always want to know the population mean, but we can't know the mean of the entire population typically because the population is too vast to survey in its entirety. So we look at a portion of it, a sample of it. We look at the mean of that sample, and that becomes the best guess for the mean of the population. What we're doing now is analogous to that. All right, so that wraps up our week 1 lecture material. There'll be some other exercises, labs for example, to start reinforcing this material. So that's what you're going to do for the remainder of the week. And then I'll see you again in 7 days' time to do this this lecture thing, this video thing, all over again. Bye for now.